On one side, the infinite inward collapse of a gravitational singularity. On the other, the outward growth of a biological neural network. Physically, they appear unrelated, yet if we measure their rhythmic pulses, they share identical geometric patterns and scaling exponents. This happens because of substrate-independent criticality. It suggests the universe is governed by deep mathematical laws that operate regardless of the physical material involved. Whether a system is made of living tissue or collapsing spacetime, the math remains the same. The mechanism driving this is a phase transition. When a system is pushed to the boundary between order and chaos, massive microscopic complexity breaks down. Billions of erratic individual parts collapse into simple, highly synchronized, unified behavior. To understand how this works, we need to trace a single foundational variable: degrees of freedom. We are going to explore how the availability of these variables constructs macroscopic reality, starting from the algebraic fuel of quantum magic up to the formation of living biological tissue. By the end, we will see that to understand both black holes and embryos, we must stop looking at the physical stuff they are made of. Instead, we have to look strictly at how their degrees of freedom collapse. For decades, physicists relied on volume law quantum entanglement to diagnose chaos and thermalization in many body systems. The assumption was that a system generating massive entanglement was genuinely chaotic. But entanglement has a massive blind spot. According to the Gottesman-Knill theorem, a highly entangled quantum state can be built using only specific Clifford gates. Even though this system looks chaotic, it can be perfectly simulated on a standard classical computer. To find true, unsimulable complexity, we need another mathematical ingredient, known in quantum information theory as magic, or non-stabilizerness. Magic measures the exact resource that alters the algebraic structure of the information, rendering the state immune to classical approximation. Static correlations alone cannot reach true quantum complexity. Instead, Clifford operations spread entanglement, while the injection of non-Clifford magic forces the entire network into a complex, chaotic three-dimensional fractal. Without magic, a system may be highly correlated, but it remains structurally simple. Magic is the true metric of quantum complexity. In chaotic quantum systems, information undergoes scrambling. This requires two distinct components: entanglement scrambling, which is the spatial widening of correlations, and magic scrambling, where operators structurally shift into non-stabilizer territory. This data maps the clear dynamical signatures that separate integrable order from chaotic scrambling. Looking at the magic trajectory over time row, magic in an integrable system rises and falls periodically. In a chaotic system, it grows monotonically until it hits a saturation point. The saturation time row reveals how fast this occurs. For a chaotic system, the time it takes to saturate scales logarithmically with the system size. This precise scaling matches the fast scrambling times found in black hole physics. Looking at the late time state row, the divergence becomes complete. While integrable systems remain below capacity, chaotic systems reach maximally magical states, saturating the entire available Hilbert space. This expansion of complexity is bounded by a magic light cone. Physicists track this through the stabilizer-Rényi entropy, watching as a simple local operator decomposes into thousands of complex Pauli strings. True chaotic scrambling goes beyond the physical dispersion of data across a system. It represents a one-way algebraic transformation away from stability. This mathematical framework of complexity points directly to the macroscopic structure of the cosmos. In high-energy physics, the ADS-CFT correspondence posits that a bulk quantum gravitational system is dual to a chaotic quantum many-body system on its boundary. This duality presented a historical paradox. Boundary entanglement flatlines quickly, yet a black hole's interior physical volume continues to grow for long periods. Entanglement alone cannot explain this geometric expansion. Quantum magic accounts for this discrepancy. Because magic exhibits monotonic growth long after entanglement has plateaued, its growth matches the persistent expansion of the black hole's interior volume. We see similar rules in ground state paradoxes. Frank Wilczek's quantum time crystals break time translation symmetry in their lowest energy state. However, a true closed system cannot spontaneously oscillate in this way without the complex multibody interactions that magic provides. As these quantum computations grow, the geometry they support grow with them. This volume expansion reveals macroscopic spacetime as a physical manifestation of underlying complexity. When we shift from the interior of black holes to the thresholds of their formation, we find the Choptuic spacetime crystal. This is an unstable intermediate state poised perfectly at the threshold between a scalar field dispersing and collapsing into a black hole. The Choptuic crystal exhibits discrete self-similarity. Its geometry repeats at ever smaller scales, governed by an echoing period delta and a critical exponent gamma. These outcomes are set by a single control parameter, energy. In gravitational physics, the amplitude of a collapsing scalar field determines the result. In living cells, metabolic energy and ATP turnover tune the system's distance from tissue-level phase transitions. A biological tissue contains virtually infinite microscopic variables. But near criticality, this high-dimensional system collapses onto a smooth, low-dimensional manifold, governed by just a handful of collective order parameters, like the global firing rate of a neural network. Unlike general relativity's fixed 4D metric, biology introduces a dynamically evolving phase space. The distribution of metabolic energy and information actively warps this biological geometry, shaping the phase space path of development. By balancing metabolic energy input against dissipation, cellular structures suspend themselves on the periphery of survival basins. They remain poised between rigid order and chaotic disorder, allowing them to process environmental noise into coherent behavior. Hovering at this volatile biological boundary enables the exact same scale-free fluctuations and power law correlations found in gravitational singularities. We can bridge these scales using renormalization group language. This framework explains how completely different microscopic parts can be grouped into identical universal classes based solely on dimensionality and symmetry. Because of these universal classes, the melting of a cellular membrane, the flocking of birds, and the ripples of a Choptuic spacetime crystal all fall into the same mathematical categories. They share identical critical exponents. Ancient philosophical traditions arrived at a similar intuition. Concepts like Spanda and Tantric Sakti described the universe not as static matter, but as a continuous, self-organizing energetic network. The 26th verse of the Mahabharata Manjari text describes awareness arising like a creeper vine to manifest a universe that operates like a machine. It is an early intuition of an emergent phase space, mapping cleanly onto our modern models. Whether we are attempting to engineer a universal quantum computer or map the evolutionary survival basins of living tissue, the triumph is the same: balancing energy and geometry to master the universe's degrees of freedom.